You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Professor Avi Loeb. Avi Loeb is a Frank B. Bird Junior Professor of Science at Harvard University, Chair of Harvard's Department of Astronomy, Founding Director of Harvard's Black Hole Initiative, and Director of the Institute for Theory and Computation within the Harvard-Smithsonian Center for Astrophysics. He also chairs the Advisory Committee for the Breakthrough Starshot Initiative, serves as the Science Theory Director for all initiatives of the Breakthrough Prize Foundation, as well as Chair of the Board on Physics and Astronomy of the National Academies. He is the author of 4 books and over 700 scientific papers. He is an elected Fellow of the American Academy of Arts and Sciences, the American Physical Society, and the International Academy of Astronautics. In 2012, Time selected Loeb as one of the 25 most influential people in space. This video is brought to you by Squarespace. Squarespace is an all-in-one platform to help you build a website and run your business. When you're working on a show that needs to be released on a regular schedule, anything that can help you save time is highly valuable. With Squarespace, creators have tools and the support needed to create content in a timely fashion. For help generating revenue from the content you create, Squarespace has member areas to allow you to hold virtual classes, workshops, or send newsletters, podcasts, and videos. Member areas help you organize and harness your online community, and if you need help, Squarespace offers email support 24 hours a day, 7 days a week. Head on over to squarespace.com for a free trial, and when you're ready to launch, go to squarespace.com/Event Horizon to save 10% of your first purchase of a website or domain.
Dr. Avi Loeb, welcome back to the program.
Thanks for having me. It's a great pleasure.
Now, Doctor, there was a paper recently released that gave yet another in a long line of perhaps problematic explanations for the mysterious object Omuamua. And you have authored a paper in response to this, that this object, they say, was emitting hydrogen, and that might have created the push in acceleration that we saw with this object. You say no. Give us an overview of your new paper.
Well, first, it's fascinating that more than 5 years after the Oumuamua was discovered, the mainstream of the astronomy community still has difficulties explaining the anomalies of it. And the anomaly that was most attended to is the excess acceleration the object exhibited away from the sun. And it wasn't clear what is giving it that push, since we didn't see any cometary tail and there wasn't the rocket effect acting on it. And that's just one anomaly out of many. I should say that in the first year, there were a number of papers written about the data that was collected, and people were saying Oumuamua looks really weird in this respect, another respect. It doesn't look like a comet. At first, they thought it's a comet. Then they said, no, it's an asteroid. Then they said, no, it's a comet. No, it's an asteroid. It wasn't clear. It had a flat shape. It had an extreme elongated shape. It was also coming from a special frame of reference. And it didn't have a cometary tail, nevertheless exhibited this acceleration. So now, more than 5 years later, another model was suggested. Now, the strange thing is, as soon as I suggested that it may be artificial in origin, the mode of the conversation changed. And experts started writing papers pushing back against the idea that it's weird, saying it's of natural origin, and in fact it's actually generic and there is nothing to worry about. And it's really strange because each of these experts came up with a different model and they disagree with each other. And in the latest incarnation, I mean, at first people suggested maybe it's a dust bunny, maybe it's a hydrogen iceberg, maybe it's a nitrogen iceberg, and each of these had problems. So One of the co-authors of the new paper is Daryl Seligman, and he wrote a paper back in 2020 suggesting it's a hydrogen iceberg. And a few months later, we wrote a paper showing that it doesn't work. That was with my colleague, Tim Huang. We basically show that hydrogen evaporates too quickly in interstellar space by absorbing the heat from starlight. And so any chunk of frozen hydrogen that may be formed in a giant molecular cloud will not make it to the solar system. And in fact, in the abstract of the new paper that just came out a few days ago, the same author, Daryl Seligman, admits that the hydrogen iceberg idea is not working. But now, with another collaborator, he proposes a variant, which is hydrogen mixed with water ice. And that's with Jennifer Bergner, and they basically suggest you start with ice, water ice, as you find in the outer part of the solar system, the Oort cloud, and then over time, as a result of the ice being exposed to cosmic rays, very energetic particles, the water molecules break into hydrogen and oxygen. And they say, well, if we work out the numbers, if you start with 30% or about a third of the water molecules being broken, then the hydrogen can evaporate when the object comes close to the sun and give the object the necessary push to explain the observed acceleration. Now, first of all, we're talking about a third of all the molecules being broken, which is quite excessive, especially since the object had a size of order 100 meters. So you need these cosmic rays to penetrate tens of meters and destroy a third of the water molecules. But nevertheless, let's assume that. And then they calculate that it gives, there is enough evaporation. But in order to find that, you need to figure out the temperature on the surface of this iceberg, this hypothetical iceberg. And they calculate it by balancing the heat input from sunlight that is impinging on the surface with the radiation coming out of the surface. So balancing the energy in with the energy out, which is the usual thing you do for a planet, for example. That explains the temperature of the Earth and temperature of Mars and so forth. The only thing they forgot is that the main motivation for their model is that hydrogen is bound more strongly to a water molecule than it is to another hydrogen atom. And that's why you keep the hydrogen atoms and not allow them to leave the system during the interstellar journey. So that's the benefit relative to having just pure hydrogen. And so now it comes to haunt you, this benefit, because in order to release the hydrogen atom, to dislodge them from the lattice, you need to invest 10 times more energy than if it was pure hydrogen. So they forgot to take that into the energy balance. So in other words, it's just like getting a salary, paying the bills on electricity and the rent and so forth, and just forgetting that you have to feed your family. And if you don't take that into account, you're in good shape, of course. And that they wrote a Nature paper saying, well, there is enough energy, everything works perfectly, the surface temperature is high, 150 degrees or so, and that allows hydrogen to evaporate, and you end up with enough push, enough propulsion. We realized that, together with my colleague Tim Huang, that there is this missing term in the energy budget. Energy conservation is really fundamental. And it's too bad that Nature magazine did not consult me as a referee. I would have flagged it immediately. That's something you immediately notice. But instead, they selected referees that are observers, very eager to explain Oumuamua as a natural object. The editor was happy. The authors were happy. They went out through the publication process and then made a big fuss in the media about it. All major journals, the New York Times, Wall Street Journal, everywhere. Scientific American, everyone celebrated the fact that here is a simple explanation that accounts for everything. And I saw the paper the same day that all of this came out. And within one day, we had a paper out saying, wait, you forgot to include the energy that needs to be invested in evaporating the hydrogen. As a result, you get a much lower temperature of the surface. We calculated it, and it's an order of magnitude lower. So we're talking about of all the 20 degrees or so, and as a result, because the temperature is so lower, the speed by which hydrogen atoms are leaving the surface is lower by a factor of 3, so they give less push through the rocket effect by a factor of 3. Then you need to actually, instead of 1/3 of the iceberg being converted to hydrogen, you need to convert everything You need to take all the water, convert it to hydrogen and oxygen. But if you convert everything to hydrogen on the surface, it resembles a hydrogen iceberg. So you didn't benefit anything. And in fact, you have the oxygen that you need to push against. So it's a worse scenario than just pure hydrogen. And moreover, at such a low temperature, it's not at all clear that the hydrogen will come out, because the temperature enables the hydrogen atoms to leave. So altogether, this scenario is not tenable at all. This model doesn't work. And of course, we shared the paper with the authors, with Nature magazine, and I'm sorry to say, with 14 other major newspapers and outlets. Some of them, I should say, very surprisingly, some science reporters came back to me and said, sorry, we just published the report about the Nature paper. We don't want to confuse our readers. What I said in response is, this is not politics here, where different people can have different opinions and both of them are viable. In science, if you claim 2 + 2 is 5, and actually 2 + 2 is 4, then the first answer is wrong. There is right and wrong in science. And if it's clear that they missed an important term in energy conservation, their paper is wrong. It's not an opinion that they expressed and we are disputing, and you can present both or just ignore ours. And so I said the oath that should be taken by science reporters is to adhere to scientific truth. They should have that integrity. They cannot just say, oh, we just posted this paper and we don't need to correct it because it will confuse our readers. Because the point is, right now they're confusing the readers. In fact, it's misinformation. And when we complain about politicians providing misinformation, let's say about COVID-19 or other matters that affect the public, how can science reporters agree to cover up what might be wrong about a report they just made yesterday? So that's my realization, which is very sober, of this unfortunate reality that we live in, where adhering to the truth, especially in science, is not a sacred principle. They could have easily just added a comment saying, Avi Loeb makes this correction based on a paper he wrote with Tim Huang, or saying, we will write a new report, which in fact, the Times in London wrote back to me and said that. So clearly the Brits have a lot of integrity.
Now, how often have you run across this phenomenon where the journals are promoting one paper over another as that in this situation? Now, of course, there's plenty of stuff the referees kick out, major journals, but when you're just posting a corrective paper like this, how often have you run into this problem?
Well, the way I see it is psychology. I mean, obviously, the journal doesn't want to admit that a mistake was made, so they want to minimize the damage to their reputation, especially Nature, which is a very prestigious journal. So they would have preferred that we would send the correction to them, and they would sort of hide it in a footnote with a small note from the author saying, yeah, we screwed up by a factor of 9 in the temperature, and that's it. But we wrote a whole paper about it, and I wrote an essay in Medium that already within less than a day got 5,000 views. So everyone, especially within the scientific community, knows about it. You cannot hide from scientific truth. If there was something wrong with our calculation, I would have heard from someone, especially the authors of the Nature paper. They would have explained it in a simple way. This silence is just inappropriate. It's much better to admit a mistake than to hide it in science, because in the long run, it will become clear. There is no way that this could somehow be hidden and forgotten, and people will just remember the original paper. So it's better to admit it if indeed it's there. And of course, the journal has an issue with reputation and so forth, but I'm talking about journalists that report about a result, and they might not be physicists. So they can say, okay, we cannot judge because we are not professionals, but they should feel an obligation to figure it out. They can speak with the authors of the paper. They can just quote me without taking responsibility. And of course, once our paper gets published, then they can report about it again. Okay, but it's really fascinating to see that the editors, the referees, and the authors themselves did not notice this. And then everyone was jumping up and down and celebrating the result without noticing it. And you ask yourself why. And of course, one possibility is that because it fits a narrative. Okay, it fits the narrative that don't worry about it. It's just a rock of a type that is very typical. Now, the reason I suspected this must be wrong is because all the comets that have a very long period come from the Oort cloud. And the Oort cloud is embedded in the same cosmic ray environment as interstellar objects because it's outside the heliosphere where the solar wind is being blocked by the interstellar medium. So basically, the solar wind often protects comets from cosmic rays, but in the Oort cloud, they are not protected. And so when they come close to the sun and we see a long period comet, then it tells us that exposure to interstellar cosmic rays would not change the cometary behavior. Moreover, I should say, the second object that was reported from interstellar space was a comet, Borisov, by the amateur astronomer Gennady Borisov. So if they claim, as they do, that you take a chunk of frozen water, pass it through interstellar space, and it turns into this hydrogen water mixture that looks really weird because you never see the cometary tail, then Borisov should not have had a cometary tail. But we saw it, it was just like a familiar comet. So clearly, the two objects are really different. And you know, what is a comet? A comet is an object that shows a coma around it from evaporated gases and dust. And that's the definition if you look at the Encyclopedia Britannica. Now, claiming that you can have a dark comet without a coma is an oxymoron because all the comets that we had seen ever had that feature. That's the way to distinguish a comet from an asteroid. And I should say that one of the authors told me half a year ago, I am writing a review, I just finished a review paper about the comet Omuamua. And I said to him, what do you mean by the comet Omuamua? We both know there was no cometary tail. How can you write a review and use the word comet when there was no comma around it? And he said, well, I have this theory that when we looked at the object at Oumuamua, it didn't have a cometary tail. When we didn't look at it, it had one. And I said, well, that's just like going to the zoo, looking at an elephant and arguing that it's a generic zebra that shows its stripes when we look away. Now, how can a mainstream astronomer claim that something that doesn't look like a comet is a comet? It's just that it shows its properties when we don't look at it. I mean, that is the level that we got to just to justify a natural origin for Oumuamua. And I say this is not the way science should be done. If you insist that the emperor has clothes, even when it doesn't, then it means that you are broadcasting to the entire world that you did not maintain your childhood curiosity because you are not honest, you are not curious, you're not asking questions about something that looks different. So if an object that doesn't look like a comet is being called a comet in a review paper, that means that black is white, war is peace, ignorance is strength. These are the kinds of slogans that were used by the party in the novel of George Orwell, 1984. And you would think that maybe it will apply to the political reality of our society, but not to science, and yet you see it in science.
If we were to take any other area of science and look for biases like this, do you think we'd find it? In other words, is there a bias against discussion of Oumuamua to pushing towards natural explanations when in fact there could be an alien explanation? And do you think that there's a bias stuck to the whole thing because the word alien was mentioned?
Yeah, I do think that the mainstream wants it to be a natural object. That's perfectly fine. You can be motivated. But when you do your science, you have to satisfy energy conservation. You have to follow the laws of physics when you make an argument. And you cannot just say that black is white. You can't use an oxymoron. You cannot say there is a dark comet and that is generic. It cannot be, the word generic cannot come up together with dark comets, because the way a comet is identified is not by not being dark, by having a comma. So you can't say that's generic. Like any iceberg made of water ice exposed to cosmic rays will turn that way, because we see such comets that were exposed to interstellar cosmic rays. And so these are really logical inconsistencies that the only way to explain them is that there is a narrative and you know what you want to say before you think it through. And that is exactly what George Orwell was describing, that you have an agenda, okay? And it brings you to a language that contradicts itself. While in politics, you might say, okay, well, that's because the politicians have an agenda. They don't adhere to evidence. They just want to convince people to follow them. In science, it shouldn't be that way. And how is it possible that now we're talking about it in the context of the last few months of an object that looked weird and is being explained with such oxymorons?
Now, the object itself, there has also been another hypothesis advanced, and this one I admittedly was not convinced by, but it was widely accepted, almost perhaps in desperation, and it was the nitrogen iceberg, where you have a nitrogen sheet lifted off a Pluto-like world, as though an impact could keep something like that intact. What's your views on that hypothesis?
Right. So first, we haven't seen it before. Okay. So the solar system does not have nitrogen icebergs that we had seen. Okay. Pluto exists. So you have to explain why we don't see nitrogen icebergs. But beyond that, if you just work out all the Plutos in the Milky Way galaxy, assuming that all of them lose their outer surface as a result of collisions, and you dislodge all this solid nitrogen from them, there is just not enough mass in solid nitrogen, if you make very generous assumptions, to explain the population of objects that would account for Oumuamua as one of them, because the statistics doesn't work out. We wrote it in a scientific paper, went through the numbers. There is just not enough solid nitrogen. So that's the problem. It's the mass budget in that case. With hydrogen, it's the evaporation. With hydrogen mixed with water, it's the surface temperature near the sun. So each of them has a challenge. With dust bunny, that is 100 times less dense than air, it's the ability of this object that is so dilute to maintain its integrity when it's heated by hundreds of degrees close to the sun. So each of these models for something that we've never seen before has its challenges, and all of them talk about objects that are natural but were never seen before. Okay, we've never seen a dark comet, so why should the first interstellar object be like that? And I say, well, if everything is something we've never seen before, why not allow for an artificial origin? And in my latest paper that I published, I actually had an idea for a possible origin that is artificial, talking about space trash, not a functional device. Freeman Dyson, about 60 years ago, came up with the idea of Dyson spheres, where a civilization that is sufficiently advanced will try to harvest all the energy output from its parent star. We are using up, even if we were optimizing clean energy on Earth, we would use up only the sunlight that is intercepting the Earth, which is a tiny fraction of all the sunlight, of all the 10 minus 8 or so. And if we were sufficiently advanced, we might have built a megastructure around the sun so that we can harvest most of its light and use it for our power consumption needs. And so imagining that is what brought Freeman Dyson to the concept. And I realized that, if you have asteroids in that planetary system, every now and then one of them will impact this structure. So as long as it's being used, it may be maintained. You may repair every time it's broken. And by the way, it could be made of tiles of light sails that are hovering above the star, the radiation pressure is exactly balanced by gravity. So that would be perhaps having tiles may be the best engineering, because otherwise you need a structure that is made of materials that are extremely tough, much tougher than we can produce. So if you imagine that, and then after, let's say, 1 billion years, the civilization moves elsewhere, or is losing interest, or is dead, or whatever happens, this structure will be broken up by all the asteroids that cross it. And you will end up with interstellar objects that are pieces from a broken Dyson sphere. And they would be thin, especially if they are made, if the original tiles were light sails. And they could, in principle, be the origin of Oumuamua. It's easier to get them expelled from a planetary system, because if they are solar sails, they were originally just hovering by radiation pressure balancing gravity. So in fact, the escape speed from such circumstances would be zero. You just need to give it a little kick and it will escape from the planetary system, whereas an asteroid is gravitationally bound to the star. So you need to give it a kick above the escape speed. In the case of a light sail that is just hovering, a small nudge would kick it out of the planetary system. So more of these pieces could escape as compared to asteroids or comets. And so that was my latest paper, and that's a possible origin of space trash.
One could imagine a situation where, okay, so you've got this Dyson swarm, a bunch of different, statites and all that sitting there surrounding the star, and then everybody goes extinct and they're abandoned. Well, it would seem to me that the star itself could kick these objects out very easily through flaring. And we know that plenty of stars in this universe flare, especially, red dwarfs and things. So it seems to me that there's a good mechanism to kick stuff out.
Yeah, in my paper, I talk not about flares, but about the evolution of the star. When the sun, in the future, the sun will become brighter, right? So if you had a Dyson sphere, let's say, for a number of billion years, and later the star evolves, most stars are billions of years older than the sun. At that point, the civilization will not stay around because it will be too hot. But those tiles, the solar sails, will be pushed out easily because now the luminosity is far greater and the mass is the same. The gravity remains the same. So that's a very simple way of kicking all these tiles out after the civilization left. And in fact, that is inevitable for such a construction.
Is it possible in your mind that there could be a situation where the reason that we don't see other civilizations, the solution to the Fermi paradox, is that we all build these sort of Dyson swarms and then we go extinct, nothing lasts forever, and that there's tons of space junk out there, but relatively few active civilizations, which is why we don't see them?
Yeah, definitely. I think it's all a question of how long the civilization lives. The method that I'm currently engaged with in finding evidence for them is just looking for packages in our mailbox or in our backyard. So what happens right now, for example, with this Nature paper is, we are looking at our backyard for the first time. Only over the past decade, we were able to detect interstellar objects. There were 4 of them. The first 2 I discovered with my student Amir Siraj, and we can talk more about them. These were meteors, roughly a meter in size. The third one was Oumuamua, and the fourth one was Borisov. Now, imagine going to your backyard and seeing objects that came from the street. My colleagues are basically saying, oh, we saw rocks in our backyard for a very long time. So anything coming from the street must be a rock. But actually, if you think about it, it might be a tennis ball thrown by the neighbor, and the neighbor may not be around anymore. So assuming that anything that enters our backyard is the same as what was there to start with is a bad assumption. We already know that most of the matter in the universe is dark, made of a substance different than what we are made of. So clearly we already know that most of the universe contains something that we don't find in the solar system. And so why would we assume that interstellar objects are the same as the objects in the solar system? And what this Nature paper tried to argue was that it's a generic iceberg of water just exposed to an interstellar journey through cosmic rays, which on a number of grounds doesn't make sense because the solar system itself in the outer parts has such objects and they appear as regular comets. And we never saw a situation where ice evaporates and doesn't produce dust that is visible and a coma that we see in the context of comets.
Now, one of the strangest aspects of Oumuamua that I saw in my mind was that it was at the local standard of rest. Would you expect anything like Borisov or something like that to actually be stuck there? How does an object that's been kicked out end up at the LSR?
So in fact, most of the objects you expect that are comets, actually you expect them to be comets because if you think about the outer part of the solar system, the objects there are floating at a very small speed. The escape speed from there is really small because they are so far away from the sun that you just need to give them a little nudge and they will leave the solar system. So most of the objects that the solar system would lose that are natural would come from the outer Oort cloud, okay? Because it's easy to kick them out by a passing star. And therefore you would expect them to be icy because it's very cold out there. And moreover, they are moving really slow relative to the characteristic motion of stars in the local standard of rest, in the frame of the galaxy. So stars move at tens of kilometers per second, 20 kilometers per second. In the outskirts of the Oort cloud extends out to 100,000 times the Earth-Sun separation. So the characteristic speed there is the square root of 100,000 smaller than the speed of the Earth around the Sun, which is comparable to the speed of the Sun relative to the local standard of rest. So we are talking about square root of 100,000 slower speed of the outer objects compared to the typical speed of the star. So that means that they inherit the motion of the star, if they are bound to it, because they don't have much relative motion compared to the star. They are bound to the star with a very low relative speed. So whenever they are nudged out of the system, they will inherit the motion of the star. So what you expect is icy objects, comets, just like Borisov, that's what you expect, that are easily visible, just like the long-period comets, and objects that inherit the motion of their parent star. Yet Oumuamua was at rest in the local standard of rest, with only 1 in 500 stars being so slow there. So the question arises as to why, that remains open. So that's one of the anomalies of Oumuamua. And, for example, if it were one out of a large number of road posts, that the spacecraft use for navigation or for communication, then, it would naturally stay in the local standard of rest or another possibility, if it wants to hide its origin. That's the best frame of reference to be in because no star is in that frame. So nobody would be able to say, oh, it's moving exactly at the speed of this or that star. So we don't know what the origin of that is. And moreover, it was very anomalous in its shape, which was flat at the 90% confidence. That was a paper written by Sergei Mashchenko, who analyzed in great detail the variation of reflected sunlight from the surface of Oumuamua. And moreover, another paper by Roman Rafikov showed that if it was evaporating like a comet, first you would see jitter because of jets. Usually comets have cavities in their surface from impacts of micrometeorites, and that's where the ice concentrates, and as a result you get these jets where you have an enhanced sublimation of ices into gas in those locations, and that causes some jitter depending on which of them are pointed towards the sun. Moreover, as the object evaporates, as the comet evaporates, the spin of the comet changes and evolves. And we haven't seen that in the case of Oumuamua. The excess push was smooth over time and there was no change in the spin period. So there was this paper by Roman Rafikov arguing it cannot be a comet. And yet again, just a few days ago, it was suggested in Nature that it is a comet. Not only a comet, but a generic comet made of water just exposed to cosmic rays. So you ask yourself, okay, what's going on here? Why do people forget all these papers? And the only reason I can imagine is wishful thinking.
Or a desire to stay away from the word extraterrestrial, which is, of course, the title of your recent book. And one coming, as I understand. Interstellar, is it?
Yes. So my next book is indeed called Interstellar. It's expected to come out in August 2023. And I just sent back the proofs to the publisher.
What is the topic of Interstellar?
Well, it has to do with what happened since my previous book was written, and that includes the Galileo project. It includes our expedition to retrieve the fragments of the first interstellar meteor, for which we are fully funded right now at $1.5 million, and we have an exceptional team of experts in ocean expeditions. And we are developing the machinery and hope to go there in the summer of 2023. Also, very important component of the book is about the implications for humanity. What does it mean for us find evidence? And my hope is, we are taking, with the Galileo project, with all my other endeavors, we are taking the road not taken. There was never a scientific project fully dedicated to this exploration. And I often say that, you have people at the extremes, those that ridicule such a search in the scientific community and push back against it, those that are believers that extraterrestrials are out there and they do not need any scientific evidence. It's just like in politics, you have polarization, but taking the middle ground, which is the most sensible thing to do, which is basically let's be guided by evidence, that approach is not very popular. And what I find is that common sense is not common. Now, what the book describes is what will be the implication if we do find low-hanging fruit in this road that was not taken, because nobody took it, therefore nobody picked up those fruits. There might be something really fascinating waiting for us to discover, especially because people keep saying that it's not worth considering that possibility. So obviously nobody is trying to collect relevant data. So my hope is we will find something that will change the future of humanity, and because it will change our perspective about our place in the universe. And I should say also it could provide entrepreneurs an opportunity to import technologies of the future. It's like a time machine, a way for us to figure out what our technological future might be, because someone else lived it already. It's not a real time machine, but it's taking advantage of the fact that some kids were born before us on our street, Cosmic Street, and they already mastered technologies that we've never dreamed about, just because their science and technology was more than a century old, like ours. And, we discovered quantum mechanics just a century ago, and now all the gadgets that we're using are based on that.
Is there any evidence to say that the interstellar objects, the two that you've been authoring papers on and trying to recover, which, good luck. I'm very hopeful that you'll find something. If these objects, which were, one of them was very harder than it should be, and that looks weird. Were any of these also at the LSR before they fell into the Earth's atmosphere? I mean, can you work that out?
Yeah, we did. So the first interstellar meteor was discovered in January 8th, 2014. And when extrapolating back in time, outside the solar system, it had a speed of 60 kilometers per second, which, it represents only the fastest 5% of the stars in the vicinity of the sun. So it was actually moving faster than 95% of all stars. Potentially, it had some propulsion, who knows? And the reason I say that is because it was the toughest meteor ever noted in the catalog, the CNEOS catalog that the US government compiled, that NASA compiled. The reason that we can infer the material strength of this object is because the government disclosed the light curve from the explosion. So we know at which elevation it exploded, and we know how much energy was released. We can figure out that it survived all the way down to the lower atmosphere, about 10 kilometers above sea level. And the atmosphere is very dense there, and it was moving really fast at 40 kilometers per second. And so we can calculate how much stress was exerted on the surface of the object, the fact that it survived, it means that its material strength is above that, and turns out to be 10 times higher than iron meteorites. So tougher than all the space rocks from the solar system seen before, by at least a factor of 10. And the question is, what is it made of? Now, the second meteor was discovered in March 2017, about 7 months before Oumuamua, both of them before Oumuamua, so they were the first interstellar objects, actually, that humans ever spotted. And then the second one was also the second toughest. So altogether, we're talking about interstellar objects having material strength that is far greater than solar system objects. And the question is why? And it's possible they originate from something else, from a natural origin, such as the collision of two neutron stars, or some other extreme phenomena that makes very tough condensations of material. Another possibility is that they were manufactured artificially. We know of stainless steel, in principle, could sustain stresses far greater than iron meteorites. And so to figure out the composition, we are going to collect the fragments of the first interstellar meteor and examine their composition in the laboratory. And then we would know whether it's a rock of a type that implies a natural origin but unusual source, or maybe it is artificial and it was a space trash. And I should say that my fantasy, I was asked several times recently, what is my wish? My wish is to go to space. And not only that, I wish that somehow the mission will not succeed, then I will be left in space and then be kicked out of the solar system by, let's say, Jupiter passing by, and then I will float in interstellar space. I will not be alive, of course. And then within 1 billion years later, I imagine my body colliding with an exoplanet that happens to be in the habitable zone of the star, and I burn up as a meteor in the atmosphere of the planet, and an astronomer on that planet says, well, look at this interstellar meteor, let's find out its composition. And then that scientist collects some fragments from the ocean floor and puts them on display in a museum. And that would be my greatest honor, to be remembered by another intelligent civilization.
Panspermic astrophysicists. In other words, life through the universe is seeded by astrophysicists escaping their star system of origin. So when you go and find an object like this, what is the end game? In other words, what if it is an anomalous object? Say it's a piece of stainless steel. We have that. Then we have Oumuamua, which might have been disguising its origin and not saying where it was from. That seems to me to be an interesting way to discover an alien civilization, is that it conceals itself from you, but not its technology. What do you think about that scenario?
Yeah, that's a possibility. I would argue most likely these are space trash. I mean, they were not functional. But of course, there are unidentified aerial phenomena that could be functional. And I was very happy that the US government shut down some balloons because it reduces the noise when the Galileo project is using its observatory to look at objects in the sky. And of course, the US government is interested in national security risks and trying to protect the safety of military personnel and citizens. But its task is complementary to the scientific mission of the Galileo project. And as a scientist, anything that has made in China on it is completely boring as far as I'm concerned, and as boring as having a high-resolution image of a bird that I'll be happy to give to a zoologist. What interests me is whether there is any object, even one, that may be from an extraterrestrial origin, and that's what we hope to find. So we should be guided by evidence, and at first we should use the known physics, because that's what we know applies to the reality that we witness every day. And I should say people overlook the fact that all of our gadgets test standard physics to exquisite precision. We use them daily and they work. And the reason they work is because there were experiments that, making them, designing them in the way that they work, and they were all based on what we know about physics. So if there was any hint of something we don't understand, then we would notice it. And in fact, physicists work for decades for very esoteric signatures of new physics, and they do not find it after investing billions of dollars. So when someone sees a hole in the clouds and claims that it's a wormhole or some new physics, that makes really little sense. First, we need to use the known physics because we know that it gives an extremely good description of the reality that we live in. And then, of course, if we have exceptional data and suddenly we see something behaving in ways we can't explain with known physics, then we should contemplate the possibility that our knowledge is incomplete. But when the Ukrainian astronomers were claiming, based on inaccurate distance measurements from one site without triangulation, that there are dark objects at a distance of 10 kilometers moving at 15 kilometers per second, faster than the escape speed from Earth, and they have a size of 10 meters, then I said, check your distance estimate, because it must be wrong by at least a factor of 10. And if you bring them closer, then they move just at 1.5 kilometers per second, and they are 1 meter in size, the typical properties of artillery shells. And if you bring them even closer, they could be bullets, or they could be birds. So I say, until you triangulate the distances and make sure that it's to a very good precision what you say it is, you shouldn't claim new physics. But instead, there were lots of people saying, oh, new physics, because, they saw dark objects and someone else saw dark objects 20 years ago. And I say, it's completely irrelevant. I want the measurement to be good before I start to contemplate something beyond the known physics. You can't argue new physics based on bad data, because then you will go around in circle all your life. You will see a hole in the cloud, you will claim that's a wormhole, and that's not the way of a scientist to infer something about reality. So being guided by evidence is really key, and evidence is collected by instruments, not by people. People are not scientific instruments, they have wishful thinking. Just think about a car accident. If you ask people involved, each of them will give you a different story. So clearly, they witnessed the same event, and yet they have very different impressions of it. The best way to figure it out is what they do in what FIFA does in the soccer World Cup. We saw that in Qatar. They have these cameras that the referees go to figure out what really happened. Okay, so the video tells all if there was a penalty or not a penalty, right? And if you were to rely on the players, obviously you'll get a different answer. So we cannot rely on eyewitness testimonies as to whether there was a penalty or not. We want to rely on video cameras that are well calibrated, that get high resolution images. And it's in exactly the same fashion. If we do it in sports, why shouldn't we do it in science? Why should people say, oh, there is new physics, we don't care about the data? Like, if you care about it in soccer, you should care about it in the case of UAP. And the way to pursue it is by building state-of-the-art cameras, just like in the soccer case, and having crisp images, having full control over your instruments, not relying on people at all. And then analyzing, in fact, we are within the Galileo project, we even use artificial intelligence to analyze the data. So even the data analysis is done by the machine, because we don't want any wishful thinking to enter. And we want to do it objectively so that AI systems will be able to classify birds from airplanes from something else. So that's the way to move forward, and we should be all guided by evidence. Now, of course, I will be the first to admit if there is no physics, that there is no physics, but unless you have exquisite data that shows beyond any reasonable doubt that known physics cannot explain it, only then you move in that direction, not with bad data.
You recently took the first step with Dr. Kirkpatrick, who heads the government UFO probe, or one of them, ARO, and you laid out the physics. In other words, an object moving through the Earth's atmosphere at this amount of speed, very high speed, according to what's reported about some UAP. should be creating a giant fireball. But I think what a lot of people missed is that also shows you the path to new physics, because if you pick up something with high quality data that's not behaving that way, that's the direction it goes. In other words, you have to explain how something's moving at Mach 30 through the atmosphere without creating a fireball. So that's what that paper did, right?
Yeah, so distances are the key, because when you see something moving across the sky, you might think that it's moving really fast, but if it's close to you, it's not moving really fast. And if it is moving fast through the air, then standard physics will say that you will get a fireball. We see that with meteors, with anything like re-entry of a spacecraft. And if you claim it's a dark object, it means it interacts with light. It means that it blocks light. So if it blocks light, it means that it interacts electromagnetically. If it interacts electromagnetically, it must respect the laws of electromagnetism and therefore interact with air, okay? The molecules of air, the electrons in the air. So you cannot avoid, if an object is dark, you cannot avoid it having friction on air. Just logical consistency within what the known physics. And if you see it as a dark object, then known physics will tell you it must be closer than some maximum distance, because the amount of light emitted by the friction with the air changes with distance, is scaling with distance to the fifth power, it turns out, because it goes like the speed cube, and then the actual area of the object that causes the friction scales with distance squared. So altogether distance to the fifth power. So that provides a very effective method for bounding the maximum distance. And if you measure the distance independently, very precisely from multiple directions, and you do triangulation, and you find that there is no fireball even though it moved very fast, then I agree with you. That may indicate new physics, but so far we haven't done that. So there is no point about talking just based on eyewitness testimonies. Just to give you an example, suppose you are driving in the highway and you see a black car in front of you, okay? And then you look at your rear view mirror and suddenly you see the black car behind you. Then you would say, that's amazing, it moves so fast. You know, it must be some new physics, but actually it's not the same car. So when people say, oh, some Navy personnel saw during the Nimitz incident, saw the tic-tac moving extremely fast, one point to another. I don't know if it's the same object. I don't have the data available. And perhaps it was a swarm of things coming in and out of view, just like the black car on the highway. How would you know unless you have the license plate? So once again, we need the data to be of high quality, under control. We need it to see the data before we can believe that there was something unusual out there. And claiming the Ukrainian report must be right because there was an eyewitness testimony during the Nimitz makes little sense. Because in both cases, the data is flawed.
Well, that's the key, is the high quality data that anybody can look at and everybody can talk about. And we don't really have that with the past accounts because there's just, you would call it fragmentary. Interesting. The Nimitz event was interesting, but we don't have a complete picture, and the government's not going to give us all their instrument
exactly.
data. So,
no, I mean, it motivates. It's intriguing, and that's why I established the Galileo project. So I pay attention to it, but I don't use it to substantiate any claims. Okay, and that's the scientific approach. If something intrigues you, you collect better data, better evidence. You know, the sky is not classified. I don't expect the US government to come out with declassification of the data they have. Perhaps they have very high quality data, but I haven't seen it, okay? My only hope is, you know, if they keep collecting very high quality data and they don't want to release it, they can just tell me, look in that direction at that time. They don't need to give me the data because I have the instruments that can see it. We have a working observatory right now on Harvard University property that is providing 24/7 images of the sky in the infrared, in the optical, and in audio, and in the future also a passive radar system. And this data comes in and we can make copies of this system and place it in many locations. So we are limited by the budget that we have. We'll make another copy by next summer, hopefully. And we are developing the software, the artificial intelligence software that will analyze this data. So if we get enough funding, what we need is tens of millions of dollars. If we get that, we should be able to get to the bottom of the nature of UAP. and doing it in a scientific way that will share our data with whoever wants it and with the public in general. Our analysis will be transparent. And so we shouldn't expect the government to be a scientific organization that is open, because it focuses on national security concerns. So we don't want to ask them to deviate from their day job. We can look at the sky ourselves. So doing it in a scientific way is the right path forward in terms of improving our knowledge about the nature of these objects.
Anything interesting so far from the instrument sitting on Harvard's roof?
We are just, it's not the roof, it's somewhere else now. No, we are analyzing the first bits of data just to test the system, make sure that we can figure out what the objects are. So we are still learning in the early stages. We don't have anything to report, but hopefully in the coming months, we'll get some interesting results. And of course, as we move forward, we can make more systems, more copies, and get more and more data. So it all depends on how much funding we have.
Now, say you had unlimited funding. Would you engage with the UFO community, the people that research this stuff and are interested in the historic accounts and everything like that, engage with them so that you might be able to decide where best to place an instrument?
We are doing that. Yes, definitely. We are looking at the reports and trying to figure out where are the best sites, definitely. I should say that any information that was gathered in the past is spotty, because no observatory of the type that we have was ever constructed. So also the instruments in the past were much of much lower quality than we have now, and the computers were of lower quality. So it's just like imagining sending a rocket to space, okay? And it's propelled by a chemical propellant, okay? So it moves at a relatively modest speed. And then decades later, you develop a new propulsion scheme. You will easily catch up with the old rocket. Even though you sent it a long time before the new rocket will move so fast that it will catch up with it and surpass it. And so you would say there is no point in paying attention to the old rocket because the new one is already beyond it. So the same I say about data. Once we collect data for more than a year with many locations, everything that was reported in the past will be dwarfed by the volume of data that we will have. Because think about it, we are getting data on the entire sky at all times, in the infrared, in the optical, in radio, and in audio. It's a huge chunk of data. And after a few years, it will be orders of magnitude more than any data ever collected by anyone. So, well, except the government, I should say. But the point of the matter is that we shouldn't look back. We should look forward.
Now, I usually don't break the fourth wall and talk directly to the audience, but I'm going to do that right now. For anybody that's interested in this topic or has been interested for how many decades, this is how you get the high quality, irrefutable data and picture of a UFO should they be out there. This is how that happens. And this is the type of data set that the scientists can look at and say, this is weird or this is mundane. And it moves out of the arena of skeptics and believers and all that, fighting about everything. This is how you get the actual real basis from which to discuss this openly and honestly based on science that you can prove, right?
Yes, I agree.
Now, Dr. Loeb, we're dealing with an extremely polarizing topic, the topic of UFOs that has raged since at least the late 1940s, and perhaps even further than that. If you invoke the work of Dr. Jacques Vallée, you see that maybe folklore in the past might be related to this somehow. Now, as a result, though, we're looking at a very polarized platform where you've got arch skeptics, very, very heavy skeptics, and which are going to criticize, and then you've also got full believers that are also going to criticize. But as they listen to this, is there a way to unite both sides? In other words, I believe it was Henry Kissinger, which I'm loath to quote him, but I think he called that détente back in the Soviet times. When you approach one side, approaches another. Is that what we have to do in order to create a sort of friendly environment to objectively look into the UFO phenomenon and see if there's something there?
Well, we have something very important that we can use, which is evidence. because I believe that if you have a high-resolution image of a technological object that shows bolts and screws and a label made on an exoplanet, and it moves in ways that human technologies cannot represent, then I don't think that a sane person that is accustomed to living in reality and not in the metaverse or in some virtual reality would deny that we are witnessing a technology that is extraterrestrial. Okay? So I believe that there is a common place where if we get there, if we get good enough evidence, everyone would be on the same page. And that's the great benefit of science, that it can bring people together once the evidence is indisputable. And that means that we need to collect that evidence. And that is the middle ground that I'm taking. Now, I get pushback from both directions. The mainstream of the science community says extraordinary claims require extraordinary evidence, and they don't provide any funding to this search. So that's a self-fulfilling prophecy in a way that if you're not searching, you will not find anything.
That's just it. You have to look at it, and you have to take a perspective that is uncolored. In other words, unencumbered by past viewpoints on the topic, the fresh start, and look at new data and try to determine if there's something to it either way, but not have any biases. So in the Galileo project, how are you taking biases? I mean, analyzing biases and saying, we need to watch out for that, we need to watch out for this, and not get caught up in that. How do you lay the groundwork for that, for true raw objectivity?
Well, the key is to collect high quality data that will basically tell us what we're seeing, and that will bring both sides to the same page. And of course, the academic community argues extraordinary claims require extraordinary evidence, but that in a way is a circular argument if you're not searching. And for that, I say extraordinary evidence requires extraordinary funding. At the moment, there is no federal funding to the search of the nature of objects near Earth that might be extraterrestrial in origin. And often, funding committees argue that they don't want to waste taxpayers' money by taking risks. And I say, just ask the taxpayers what they're interested in. Are they interested in the search for dark matter more than the nature of unidentified objects or extraterrestrial gadgets? And the answer would be 60% of the US public believes in extraterrestrial life, therefore they would find that to be the most exciting scientific research agenda that their taxpayers' money can be used for. It's a really strange reality that we live in, whereas the mainstream of the scientific community is blocking funding and claiming that there is no evidence. So that's inappropriate. And of course, I broke that mold by getting funded by the private sector. So I don't depend on those committees. But at the same time, you have the groups of believers that do not necessarily adhere to the scientific method of collecting data before coming to conclusions. And I say that's inappropriate as well. And obviously, the two extremes are fueling each other, just like in politics. If one side makes a very strong statement, the other side shies away from it with an equally strong statement. But the actual challenge is to walk in the middle and bring them together. And the best way to do that is by collecting evidence that both would agree is conclusive. And that's the way we should proceed. And that's the spirit of the Galileo project. And that's the path that I'm taking. I'm very intrigued by what was reported in the past. That's what leads me to take this path. But I don't draw conclusions without getting the evidence. And it's, I'm a theoretical astrophysicist, so I worked in theory primarily, but I'm leading an experimental project because otherwise it will not be done. And so let's see what we find, and everyone will witness the same information that the Galileo project is collecting as the team members are witnessing. So we will make our data open, the analysis transparent, and hopefully will advance in our knowledge.
Hypothetical materials. So in this search, if you see something that seemingly is violating the laws of physics, maybe not, because there are areas of physics that are quite hypothetical. We've never seen them, but maybe. And one of those is negative mass. which has been around for a long time. I think it was first advanced by physicist Herman Bondi, many years ago, and later expounded on by Robert Forward and others. This idea of negative mass, could you give us an overview of that?
Well, we don't know if it's possible to engineer it, but if you had a negative mass, it would mean that this object repels gravitationally a positive mass next to it, rather than attract it the way the sun attracts the Earth. And so just imagine two masses, one being negative and the other positive, of equal magnitude. So the negative mass will push away the positive mass, and the positive mass will attract the negative mass. And you will end up with the two of them accelerating as a pair together to arbitrarily close to the speed of light, because you keep having the force that each of them exerts on the other. And there is no violation of energy conservation here, because the kinetic energy of the negative mass is negative, so the sum of the two energies is zero. But if you imagine that being an engine for a spacecraft, this spacecraft could, in principle, reach very close to the speed of light. So just imagine the Earth, a planet like the Earth, which is the positive mass, and then next to it, an equal but negative mass. And if it's very close to it, then the gravitational acceleration will be roughly 1g, the same acceleration as we feel on the surface of Earth. So in principle, we could live through this journey, because we would feel an acceleration similar to the one we feel on the surface of Earth. And if you accelerate at 1g for a year, you end up near the speed of light. And if you keep accelerating at 1g beyond that, beyond 1 year to maybe several decades, you come so close to the speed of light that you can traverse the entire universe over a human lifetime, just because of time dilation. Time is ticking much slower in that accelerated frame. So if we can build such an engine, we can sell tickets to a trip across the entire universe during a human lifetime. And of course, the rest of the universe will age by billions of years during that time. But the people on that spacecraft will just age as usual, but will go across huge distances. So we are not violating anything. There is no motion faster than light. It's just time dilation that allows the journey to go across large distances over a time that appears to be manageable for humans if they're sitting inside the spacecraft. And the question is whether any civilization engineered such a negative mass. And I'm currently working on a paper where we imagine circumstances by which you can do that, by using some scalar field and building it in a way that will create a negative mass. So even though Herman Bondi thought about it in 1957 and Robert Forward elaborated in 1990, there was never a physical solution that explained how to make such a negative mass. But it's quite possible that another civilization, far more sophisticated than we are, was capable of accomplishing that. And then, of course, that kind of a spacecraft will move really fast in our neighborhood. And astronomers are not monitoring objects moving close to the speed of light, because they would introduce just one image in any survey of the sky, and you won't know whether it's just a fluke. So astronomers ignore objects moving so fast, and they look for objects that move 10,000 times slower than light in the solar system. These are the rocks that are bound to the sun. And I argue that in the future, we should pay attention to objects moving much faster, because maybe someone is having or using such an engine. By the way, it doesn't violate the laws of physics. This paper we're writing is based on what we know. It just goes well beyond what we can technologically manufacture right now. The other thing that we are not monitoring are small objects that are reflecting very small amounts of light. We noticed Oumuamua, which was the size of a football field, but most of the objects we send to space are much smaller. The CubeSats are several orders of magnitude smaller than a football field. So perhaps there are objects passing in the dark, so to speak, near Earth. We don't see them because they're so small. They don't reflect much sunlight, so our telescopes cannot pick them up. But there might be a large population of such objects. And I say that our surveys are very limited as of now. We only had the capability of detecting interstellar objects over the past decade. So we should now pay more attention to this subject and invest in it. And if I had an infinite funding, then I would allocate much of it to studying our cosmic neighborhood, our backyard, for any objects moving really fast or having a very small size. Of course, the other thing I would invest in is exploring space, because if you just take the amount of money we spend on military budgets, which is $2 trillion a year, and allocate it to space exploration, then you could, in principle, send a probe to every star in the Milky Way galaxy within several decades. That would be remarkable. If we became a peaceful space exploring civilization, that would mean that finally we paid attention to the words of John Lennon, "Imagine all the people living in peace." And all it takes is not to invest most of our funds in killing each other.
Well, I can agree with that. No more war. But to get into the strange physics. So if you have two objects bound to each other, one of negative mass, one of positive mass, traveling at near the speed of light, arbitrarily close to it, time almost stops. So does this solve the communications problem, the speed of light communications problem of two civilizations talking to each other simply by time dilation, meaning that you could have communication between one traveling civilization and another traveling civilization, and billions of years are passing, but not for them in their frame of reference. So in other words, communications of, the SETI nature might actually be easier if you're traveling at very high speed, right?
Well, the light that is being sent, the signals have to catch up with the spacecraft. So if it moves really fast, close to the speed of light, it will take more time for the light to catch up with the spacecraft. So it doesn't solve that problem of communication. It does solve the problem of allowing humans to travel across huge distances because time is ticking more slowly in their frame. That's one of the benefits of the special theory of relativity. And obviously, anyone left behind on Earth would die, and in fact, Earth itself will be burned up by the sun by the time they get to the edge of the universe and maybe even come back. But for them, only a few decades would have elapsed. It's one way to get to our future relatively quickly, in the sense that you don't need to freeze your body, you just need to move close to the speed of light, and then time will pass much more quickly elsewhere. And then when you come back, you will live in the future.
Now, within relativity, the idea of being able to do this, now, contraction of time and actually stopping it. Recently, I had a conversation with someone about how photons don't experience time. Does this tell you something about the Big Bang, the nature of reality itself, in that if time is a variable, a something, so to speak, like space might be a something and it's expanding, that sort of almost, doesn't that point to a model where maybe there is some point where there are no dimensions of space and time, and that this might be an illusion, the three-dimensional world?
Well, we cannot conceive of a reality that is not embedded in the three dimensions of space and one dimension of time. Of course, there are physicists imagining that there are more dimensions out there. That's in the context of string theory, or in fact, there are other parts of the so-called multiverse where conditions are quite different. Maybe the laws of physics are quite different, and who knows what can change. But, we can imagine things. The only question is, what is the reality that we all share? And otherwise, it's fantasy land. Now, of course, what we see may be a reflection of conditions under circumstances that we've never witnessed. If we find packages from another civilization, they might tell us that conditions are really different and our experiences are not shared by everyone very far away. It's similar in a way to Plato's cave allegory, where there are prisoners that are chained to a cave, and all they see are the shadows because there is a fire lit up that illuminates things behind them that they can't see, and they see the shadows and they have to infer what the shadows mean. And for them, the reality that they can see is only in the form of these shadows. We are chained to the earth by gravity, and we spend our life on earth, and we end up on earth. So all humans so far died on this earth from where their body was nourished. But so we are sort of like those prisoners, except the chain is gravity that keeps us locked here like prisoners. And if we see extraterrestrial gadgets, if we see some packages from other civilizations, they might be the shadows of those civilizations, especially if they have artificial intelligence that somehow echoes those civilizations. We will not encounter the actual civilization, but we'll encounter the shadows of that. And of course, the reality may be quite different than the shadow would imply. And the role of the scientist would be to figure out what it means. And we can use AI systems to interpret their AI systems, just to figure out where they came from, how they were constructed, what kind of tasks they are seeking, what kind of information they are seeking, why are they here? Lots of questions. And those would be the second layer of our learning experience. The first layer is simply noticing them. That's what the Galileo project is all about. Noticing them, seeing something different than natural objects or human-made objects. And then will come the most challenging task of figuring out what it means.
We have always run the risk, and nobody knows this like the dinosaurs. We've always run the risk of an object hitting the planet and causing a mass extinction event. Is it possible that we've missed something and that objects, whether it's natural, maybe shot out by a supernova or something like that at relativistic speeds, or artificial, an alien civilization traveling through, and then they make a mistake and they're just stuck traveling at high speed? Can an object hit Earth at relativistic speeds and take us out?
Not really. The only thing that can happen is an object passing through the atmosphere can scoop up some microbes from the atmosphere and carry them as tiny astronauts. But it's impossible to sort of jump on ship if it moves so fast without your body being destroyed, because it will burn up, your body will burn up from the relative speed if you were to collide or try to jump on such an object. You really need to come close to the speed of the object before you jump on it. That became apparent from the science fiction movie Gravity that showed the astronauts jumping from one spacecraft to another. Of course, that's not practical. You really need to move at a speed that is very close to the speed of the satellite that you want to hop on. So no, the answer is no. It needs to slow down, needs to perhaps have a parachute, land on Earth, and then, of course, it could, in principle, be fueled and leave Earth just like our rockets do. So you could board a spacecraft. And about a decade ago, I was asked by a journalist, what would happen if a spacecraft landed in your backyard? And I asked my wife, and she said, well, just if you want, you can go ahead and board it as long as you leave the car keys with me. And I must say that we made progress in our marriage life, because now she says, I will just ask you to turn off the lights and I'll join you. So, it would be fascinating, of course, to leave Earth with a vehicle that is far more advanced than we possess and see what's out there. I would love to do that. When I asked my students at class, they said that they're willing to do that only if they will be able to share their experience with their peers, through social media. Only then they would go up, if they can use Snapchat or Instagram.
Now, my last question for you is something a little different. And it's something I think about a lot as a science fiction author. If you could go out into space and go anywhere, what natural vista would you most want to see? And I will give my answer, which is I want to see an accretion disk of a black hole relatively close. If you could go anywhere as an astrophysicist, where would you go to just to take a look?
The most advanced technological infrastructure that exists in the Milky Way galaxy. And I'm not aiming to any other galaxy simply because the universe is accelerating. It will be really difficult to make the journey unless you have this negative mass engine. But I really want to see the most fascinating gadgets out there, because even within our civilization, that's what intrigues me. Whenever a new technological equipment comes forward, I really want to own it, to use it. Now it's Chat GPT-4 that I enjoy, and I'm always excited by the latest and the most advanced. And of course, what we have here on Earth is quite limited, and I would love to see the product of a technological civilization that had its science around for 1 billion years. It's amazing what it might be able to do. Maybe they can create a baby universe. Maybe, obviously, they would be able to create life. I'm pretty sure of that. We can learn from them. And moreover, it sort of unifies religion and science in the sense that you would see someone far more capable than you. And it looking at what it can do brings awe to your life, sort of like a religious experience. And I think that's our opportunity to learn something from a smarter kid in our cosmic neighborhood.
Maybe that is the great unifier. The discovery of alien life shows us that we are the humans. We are the earthlings, as it were. And maybe that's what helps us get past the great filter is contact itself, and maybe they do that intentionally. You get a radio signal from SETI or something just to tell you, hey, get everything together. There's something out here.
Yeah, what you just described resonates with a significant fraction of my forthcoming book, Interstellar. So I encourage you to have a look at it when it comes out.
I look forward to it. Thanks once again, Dr. Loeb, for joining us, and we'll check in again in the future. Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.